Hello everyone, welcome to Statistical Methods. In this video we'll be talking about how to estimate regression coefficients in the linear model. In particular, we will be focusing on the method of least squares and on maximum likelihood. If you would like to read about this in the lecture note, then have a look in chapter 17. So let's get started. So in this session we'll talk about two ways to estimate regression coefficients, and the two most important ways. So the very simple way to estimate regression coefficients is a way called OLS, or ordinary least squares. So what is ordinary meaning? So ordinary means it's not weighted, because there's also weighted least squares. So that's the method we'll use first, and then later we use maximum likelihood and see how this both methods are linked. So this way to estimate the regression coefficient goes back to Gauss and to Legendre. So I think Gauss developed this in 1805 and Legendre 1809. So about 220 years old. And the idea is we minimize the squared error and by minimizing the squared error, so we get values for the parameters. So we have an optimization problem, and for the regression it looks like this. So we have, in simple linear regression, so we have x here and our y here, and then we have our linear model here, and then we have data points. So each data point is a sample, of course, from this regression model, where we have this deterministic part and the noise part. And now what we have here, so this is our data point, and this data point consists of x, I, y, I, so it's a pair, and let's say this is y10 or an x10, and this one would be 1, 2, 3, 4, 5, 6, 7, 8, 9, so it's in fact 10. And what we're trying to fit now, so this is our curve here, so this is our y equals beta naught plus beta times x plus epsilon. So that's our regression model, and what we're trying to fit now is the difference, squared difference of the deviation of these predicted curve here. So these differences here, so this thing here, when we fit this thing, we actually have estimated quantities. So we have beta naught estimated plus beta hat estimated times x plus epsilon, and then this thing here, let's just for a moment remove the epsilon here so that it's correct. So this thing then becomes the where is my point. Oh, okay, it's here. So this thing where is it? It's not drawing. Okay, sorry for that. So this thing then becomes the predicted value for x. So this is our predicted. So these things here, what we have here, these points are the predicted y hat I values on this line. So they form the predicted line. So y I is xi times beta naught hat plus beta hat x1, and then the difference epsilon I are the residuals, namely the y hat I minus y I, and the y hat I is of course beta naught hat plus beta hat xi minus yi. So this is called a residual, and the aim is now, so aim in ordinary least squares is we determine optimal beta naught hat and beta hat by minimizing the sum of squares, namely the sum I goes from 1 to n of epsilon n squared. So that's what OLS is doing. And so we're trying to minimize the sum of squares. Minimize, we call it the residual sum of squares. So that's how it's called. And the residual sum of squares, this is abbreviated as RSS. So this is now the component notation. We can actually write it in matrix notation. In the statistics convention, so we can write beta is our vector of beta 1, beta naught, beta d. So let's say we do it now for multiple regressions. So beta is our, and we assume that beta naught is 0, just for convenience, because we've seen in the last video that you can center y and x, and then beta naught becomes 0. So this is beta just tells us whether it goes through the origin or not. So we can write the residual sum of squares as a function of beta as follows, namely as the y vector. So this is the vector of observations minus the data matrix vector times beta transpose y minus x beta. So you can, just for a reminder, so y here is y1 to yn, x is a matrix, so that's y is n times 1, x is a matrix n times d, where we have x 1 1, it goes to x1d, and here we have xn1, and this goes to xnd. So where we have in the rows the samples, and beta we already have here, so that's our vector containing the regression coefficients. So this is our residual sum of squares independent of beta. Then beta hat OLS is the beta set of beta that minimize this thing, and we can try to minimize it by just computing the gradient. So we can write the residual sum of squares of beta is y transpose y minus 2 beta x transpose y. So we just multiply out this product here. We have b transpose x beta. So that's our function. Now we can compute the gradient. The gradient would be the first order derivative with regard to beta, and that is simply minus 2x transpose y plus 2x transpose x beta. And we set RSS equal to 0, then we know that we have an optimum, and this leads to the solution that xy equals x transpose x beta hat, and this gives immediately the solution beta hat OLS is x transpose x inverse x transpose y. So that's a very, very famous estimator, and you should actually memorize this estimator. So it's the Gauss estimator, and when x is a centered data matrix, so x centered and y centered, then this is the estimate of the regression coefficient, and this estimate minimizes the mean squared error. The interesting thing is that so OLS, of course, seems ad hoc, but it actually isn't, because as we will see, it's basically a version of maximum likelihood. It's a special case of maximum likelihood. And that's why it's important. And so it shares, you can see that it shares the derivation, shares commonalities with maximum likelihood. So we found a minimum. So of course we need to check whether this is actually the minimum. So if we go one step further, we can find that this is the minimum, so that's not a problem. So we had an objective function that we were minimizing, and next we'll see that this is corresponding to a certain maximum likelihood function. So let's continue. So now you know how to do it in practice, and this is when you run R. So when you run R in R, if you run LM, will give you the above estimator, will return the above estimator. So one thing that is important here, what you see here is you have actually X transpose X inverse, and as we will discuss later, this is linked to the covariance matrix of the predictor, and since we invert, we would like to have this positive definite, but we'll come to that in due course. So let's continue with maximum likelihood. So ML estimator of regression coefficient, and that actually proceeds more or less in the same fashion. So we have the regression equation again. So let's write down y is beta naught plus beta x. So now I'm writing it down in the random variable notation. No, this is actually not a vector. These are all scalars. The only thing that's a beta is, of course, our beta is beta 1, beta d, and x is x1, xd. So, and we have the expectation of epsilon is 0, and we have our observed data. So we have data y1, yn, and we have x1 to xn. So you see, in contrast to above, before we used the matrix notation, now we use vector notation. So this helps now to figure out what the intercept is. So the intercept, of course, is beta naught is mu y minus beta mu x. And to see this is simple. We just take the expectation on both sides. So take E on both sides, and you get this because we know that the expectation of epsilon is 0. So, and then we also get the epsilon. So we get for epsilon is simply y minus mu y minus beta transpose x minus mu x. So this also follows from the above. Okay, so this is just because in maximum likelihood we also look at the distribution of epsilon as well, not just for y and x. So with this we can now actually compute the joint model, or joint, we assume a joint model for y and x. So in maximum likelihood we need to assume distributions, so we assume joint normal, multivariate normal for y and x, and this leads to the following ML estimators. Namely, we get, for the estimator of the mean of y is simply the estimate of empirical mean of y, which is the average, of course, so it's 1 over n yi, and I goes from 1 to n. Then we can also compute the variance, the corresponding variance y, and this is the empirical variance of y, and note that I'm using 1 over n. Then, so that's for the y. We can compute, similarly, we can compute the mean for the x. That's the empirical mean, so 1 over n. Then we can compute the covariance, sigma xx. And that is, so these are just the standard formulas. I mean, we've calculated them already earlier when we looked into multivariate normal and normal distribution. So the estimate of the covariance so note these are all vectors, and this is a d times 1 vector, and this is a 1 times d vector, so the whole thing is a d times d matrix, as it should. And then finally we can also compute the covariance between x and y, or the estimated covariance between x and y. So it's cov x, y. And so these are all the typical maximum likelihood estimators, where we replace the expectation by the average. So this is the following. So it's the same as above, only that we use mu x, and we also have here y minus mu hat y. So, and then we get, this is a d times 1, and this is 1 times 1, so the whole thing is actually a vector. So this is a vector, d times 1, or d times 1 vector that we get here. Okay, so these are the simple things. Now we can, so far we have made assumptions about x and y, and now we also need to have a model for the noise, and the assumption was the noise is independent of x. So, and we assume that the noise is all the eps I are from the normal with mean 0 and some variance, some noise variance. And this one is now the model that we use for fitting the regression coefficients. So the log likelihood of this model is minus n half log sigma epsilon. So that's just the normal thing, the usual likelihood when we have a normal distribution, and fixed mean 2 sigma epsilon squared, and then the observations are our residuals. So the residuals are actually from this, drawn from this distribution. And this is where the beta hat and the beta naught come in. Or actually not only beta, because beta naught we already basically estimated here right at the beginning. So that's our beta naught. So this contains beta, so this becomes minus n half log sigma epsilon minus 1 over 2 sigma, and then we have the sum I1 n, and then we have yi minus mu hat, y minus beta transpose xi minus mu hat x squared. So this is just the definition of this epsilon a, and it turns out that this thing here is simply what we had before in the OLS. So this is our residual sum of squares. So these are the OLS residual sum of squares. And in the residual sum of squares, so in ML, maximize log L, and you see this minus here. So because we have this minus here, is the same as minimizing the residual sum of squares. So it's exactly the same thing. And then we get estimates of the ML estimate of the beta ML, and that turns out that is exactly the same thing as before. So we get beta hat ML, so this is of course a vector, is sigma x hat minus, so the inverse times sigma hat x y. So that's the ML estimate, MLE, for the regression coefficients. So you find further details, and so you can also, if once we have, so we have the estimators of plus estimates of mu hat x and mu hat y, and this leads to beta naught hat ML as mu hat y minus beta hat transpose ML mu x. So we have estimators for regression coefficients and for the intercept. So we have estimate for beta and beta naught, and at the same time we get estimates for everything else. So we get estimates for the noise. So we have the estimate, the maximum likelihood estimate of the noise error, and that turns out to be simply the residual sum at the ML divided by n, because it's simply 1 over n of the differences between yi minus y hat I. So the residual sum of squares divided by the number of samples is simply just the ML estimate of the variance of the noise. So RSS is estimate of noise variance. And of course what we do here by minimizing, so we try to minimize the noise, maximize signal, basically. So that's what OLS, this is what OLS is doing, and also what ML is doing. So the good thing is, so ML and MLE for regression equals OLS, assuming normality. So if we have a normal distribution and we do maximum likelihood, we end up doing ordinary least squares. So in this case, OLS is a special case of ML. And in fact, if you go to more advanced courses, so other regression models, for example, generalized linear models may assume other distributions. So GLM assumes that it's from the exponential family, so it's still easy to solve distribution. But then, of course, OLS is not the same as maximum likelihood. So, but we only discuss simple linear regression. In this case, the maximum likelihood assumes normal, and then we end up doing the OLS. So advantage of maximum likelihood is, of course, is that we have a optimality for a large n. So if we have a lot of data, then we have the correct estimator. And B, we know asymptotic distributions for the estimator. And we can do the same thing for our regression coefficients, and the details are in the script, so just summarize them here. So we can show that the variance of these regression coefficients is actually, so the related to the inverse of the covariance between the predictors. So it's the noise variance times the inverse of the predictor variance. So, and this also shows, so if the noise is high, then the variance is high, and likewise the precision, so the inverse of a covariance matrix is called the precision. So the correlation between the predictors have an influence about the variance of the, or covariance of the predictors, and the variance of, there's a similar expression for the variance of the intercept, for instance. So, and so that I write it down, the variance of beta naught, the estimated beta naught, is the similar expression is 1 over n, and then also the estimated noise variance times 1 plus mu transpose sigma x minus 1. So that's related to it. So these are of course vectors, and this is a matrix. And then why do we want this? So we now have an assessment of the error of beta hat and beta naught. We can construct confidence intervals, and of course we know the distribution, the asymptotic distribution, which is of course multivariate normal. So we know that beta is distributed as multivariate normal around the true beta with the variance of beta, and we know that beta naught is distributed normally on beta naught and the variance of beta naught. And this, of course, we can then use, if we like to, we can use this as null model to test whether beta is 0 or beta naught is 0. So that's why it's useful to have this distribution, because we can actually get approximate p-values whether the regression coefficient is 0 or not. So that's it for today. So you'll find this in more details in the script. In the next video I'll explain 3 more methods to estimate the regression coefficients, and these 3 other methods will also help to further understand what's going on in the linear regression model. So see you in the next video, and until then, bye bye.